Cancer is a very common disease. In fact, approximately 38.4% of men and women will be diagnosed with cancer at some point in their lifetimes. To understand it, think of the body like a game of telephone. The word that's being passed around is like a cell's DNA, its instruction set. If one of the player's cells can't quite hear it, then they'll pass forward the wrong word, and so with the next cell and the next and so on. In the case of cancer, the wrong word is telling the cells to reproduce indefinitely. Normally, your body removes these broken cells through a process called APOPTOSIS, or programmed cell death. It's like the body's spam folder, how it discards unwanted or harmful material. In order to tell cancer cells from healthy cells, the immune system has what are called checkpoints, signals that say yes or no to apoptosis. Cancer cells, however, find a way to evade this process and keep popping up in your inbox by producing chemicals that will bind to T cells, our main immune system cell, and tell them no instead of yes. What's worse, they can spread to other tissues and areas of the body and compromise them too. We can try to kill these bad cells through chemotherapy and radiotherapy. The problem is your body's like a garden. If you try to remove pests with pesticides, you might end up killing flowers too. Chemo and radio kill cancer cells, but also many healthy cells. But what if instead of targeting the pest, you could help out its predator? In our bodies, the natural cancer predators are immune system cells. As you know, however, T cells have a hard time telling between tumor cells and healthy cells. For that, we introduce immune checkpoint inhibitors, chemicals that can block tumor antigens and break the cancer's disguise. You could also inject fragments of cancer cells in order to stimulate T cells, or even genetically engineer antibodies in T cells that will only target specific cancer toxins. Boosting the immune system to treat cancer is called immunotherapy. But the main problem with immunotherapy and any sort of treatment for cancer is that there's a general lack of control. When a drug is injected into the human body, it could get destroyed by the immune system or even react with cells it wasn't meant to. There's also something called the tumor microenvironment, or TME, which is a very specific set of conditions that the tumor builds to promote its own growth, while keeping anti-tumor agents out. Also, we have no control over drug exposure time. This is a problem because cancer drugs are like a hot sun. Stay under it for the appropriate amount of time, and you get vitamin D and maybe even a nice tan. But stay there for too long, and you end up with some nasty side effects. This is where we could get the help of nanotechnology. And no, we're not talking about super small robots that we're going to pilot through someone's body. These are capsules that are 1,000 times smaller than human cells and can infiltrate through tumor blood vessels. The catch here is that we can tune their membranes so that they respond to different stimuli such as light, pH, or temperature. So, if we know our TME, we can adapt our capsule to only disintegrate around those conditions. This way, the drug will remain protected until it reaches the desired region, providing a much more local and effective treatment. The future is bright. Nanotechnology may still be something relatively new and definitely have limited access, but research is growing and new drugs are going into the market. And although we're not sending microspaceships through our veins, if you ask me, this is something much, much more exciting.